hear us?
Yes, I can hear you.
Perfect. All right. So you can start sharing, and all the while we're gonna, but put the camera on as well. Perfect.
Just hit the X there for the recording.
Okay, so I can start whenever you want.
1 second. Arnaud is gonna give you a presentation of yourself.
Oh.
Very short. Yeah. Please join me in welcoming François Paco, an assistant professor at the Centre Automatique et Système at Mines Paris PSL. His work advances large-scale mathematical optimization with a focus on interior point methods for nonlinear and stochastic programs. He earned his PhD at Ceramics, École des Ponts in 2018, and was a postdoc in Argonne's Mathematics and Computer Science Division from 2020 to 2022.
Indeed.
Thank you.
Thank you, Arnaud, for the introduction. So I guess I can start now. I'm very excited to present this lecture. Andrew, you were saying something?
Yes, Ed, the floor is yours.
Oh, excellent. So I'm quite excited to present this today because, I mean, it has been a lot of work just to get where we are at now. So I would like to share with you how we have done that. In particular, today I will focus on how to use GPUs for optimal control. So as you know, I'm currently developing a nonlinear solver called ManNLP. So of course, I will look at optimal control from a nonlinear programming point of view. So I will explain in this lecture what is nonlinear programming for me and what is optimal control. And then I will give some results showing the performance of GPUs to solve large-scale optimal control problems. So feel free to interrupt me during the lecture. I will be happy to take any question. So let's go. So of course, I'm not alone. I'm part of a larger team. So we are now called MathSuite because we are developing a whole suite of solvers for all based on the interior point method and all running on the GPUs. So I'm working mostly with Alexis Montoison, who is currently a postdoc at Argonne, and Sungo, who is currently assistant professor at MIT. And I'm also still working with my former PI at Argonne, Mihai Enitescu. So as I just said before, today I will mostly talk about GPU-accelerated optimal control. So I will present what is an optimal control problem for me, and how I do interpret that optimal control problem as a nonlinear program. And then I will use ManNLP to solve that nonlinear program. And I will finish the lecture by presenting some extension. By that, I mean how to exploit the dynamic structure in optimal control to accelerate further the speed of to get a solution. So I have two main motivations for today's lecture. I think you are all well aware of that. So the first motivation is, I mean, there is a new generation of optimization solver underway who are, I mean, all these new solvers are all exploiting the GPUs. So just a piece of advertisement. So there is like a workshop at the next RIPS conference called Scale Up for GPU accelerated and scalable optimization, where Sungo will give a talk. So I highly advise, if you go to NeurIPS, to attend Sungo's talk. So that's the first motivation. So I will present what do I mean, what are the other optimization solvers in the third section. The second motivation is, if you look at the bigger picture, right now there is a huge interest in robotics, what they call physical AI. I don't like that term, but they like to use it in the press or anything. So NVIDIA and other companies are pouring a lot of money into robotics. So the question is, how can we use GPUs to control robots? If you look at how do they do that, actually, so it's either they use reinforcement learning. So I won't talk at all about reinforcement learning because I'm not an expert on that topic. Or they use model predictive control. So they explicit the dynamic of the robot and they find the control by solving a QP or a nonlinear program. I think Enrique Ferrolo gave you a presentation about that second approach before during that set of lecture. So NVIDIA is developing currently small GPUs for robots. For instance, NVIDIA Jetson. So they have low power consumption, so they are not as powerful as the other GPUs we can have in clusters or in the cloud, but they can be quite useful to run MPC algorithm. That's for the motivation. So that's the outline of my talk. So I will first detail what is optimal control for me. So I think here you will hear a lot about what you have seen before during that lecture. So I mean nonlinear programming, I mean LQR, I mean controllability, all that stuff. And then I will present the interrupt method, which we are using inside MadNLP. So I'll go in length into that because it's very important for us. We get all the performance using interrupt method right there. So I will spend a lot of time into that section. Then I will do some linear algebra. I will explain how to depart the linear algebra on the GPUs. And last, I will go through some numerical result. Any questions so far?
I think we're good.
Excellent. So in that case, I will continue and start writing some math. So what is optimal control for me? So to me, optimal control, it's a way to find some optimal trajectory. So I usually consider a physical system with a dynamics. So I don't know, for instance, if you take a robot, you can describe the dynamics of your robot using a set of ordinary differential equations. Then you can discretize this equation and solve an optimization problem to find the optimal trajectory. So it's mostly used for trajectory planning. So it's mostly in the, for instance, in the space industry, that's how they compute the trajectory of rocket. Or it can be used for real-time optimization using what we call model predictive control. So both problems, they are not exactly the same, but they both have a dynamic structure, right? So model predictive control, I think it comes back to the 70s, because back then people were trying to save energy or save money because it was like the oil crisis. And they started developing that kind of method during the 70s. And I give a lot of credit to Larry Bigler, who did a lot in the chemical industry in the 90s to develop model predictive control. So for instance, model predictive control is widely used in oil refinery. Because if you look at a refinery, the dynamic is quite slow, much slower than in a robot. So it was much easier to deploy model predictive control in that industry than in robotics. The good news is now the computers are powerful enough, we can run model predictive control at a very high rate. By that, I mean 100 times per second. And that opens new doors for model predictive control. So by that, I mean we can address system with a faster dynamics like robot. So here is just a small example. It's just you have a satellite and it has to reach a given target, for instance, to change the trajectory. So I just start the satellite on a circle. So here you get an initial position, a second initial position, a third initial position. And for each initial position, I just compute the optimal trajectory to reach the target. And it's quite usual in optimal control to get a set, I mean, to describe your solution as a set of trajectory to the final point. Right. So that's exactly what I depict in that figure. So as I just mentioned, optimal control is not a new field. There are already a very good ecosystem to solve optimal control problem on the CPU. So the classical workflow is usually you model your problem with some framework or some modeler. So most of the time people are using Casady, which is very good for optimal control. I mean, it's much better than Jump, for instance. As soon as your problem has a dynamic structure. And the problem is modeled inside Casady. Casady transcribes the problem and pass a set of callback to IPOpt, and you can solve your problem with IPOpt very efficiently. So IPOpt can be interpreted as a backend and Casady as a frontend. Actually, IPOpt got a lot of users from Casady. that's one of the reasons why IPR got so popular in the last 10 years. That's for the ecosystem. So what can we do now? So first, I would like to acknowledge some very useful books that I use a lot to prepare this lecture or in my other teaching. So I highly recommend having a look at this book. I mean, it's very well known in optimal control. It's called The Horizon on O. And here you have everything. You have nonlinear programming, you have dynamic programming, AQR, everything is covered, and it's actually quite easy to follow. I think it's one of the best references when it comes to optimal control. I really like the book by John Betts, Practical Method for Optimal Control Using Nonlinear Programming. It's not as good as the Horizon on O. I mean, you don't have as much contents, but it's more up to date. So here it describes how to use a nonlinear solver to solve, I mean, any optimal control. And you have a lot of consideration about numerical linear algebra inside that book. So of course, I like a lot the book by Lawrence Bigler, Nonlinear Programming. If you would like to understand how does IPOT work, just read that book. And last, I would like to analyze this famous book by Rawlings, Mann, and Deal about how to do model predictive control. And in that book, everything about model predictive control is covered. So if you read these 4 books, you are covered. You can solve any optimal control you want. So just to give some acknowledgement, I mean, this lecture is not made out of nowhere, right? I have to give credit to the people who were there before me, and who are still there, actually. So what do I mean exactly by optimal control? So first, I would like to acknowledge something, to be very explicit. So we will work exclusively in discrete time. I won't deal at all about system with a continuous time dynamics, because I don't want to do any analytics. I prefer to write things in an algebraic way. Anyway, at the end, what we want to do is to solve the optimal control problem on the computer. So that means we have to write everything in bits. So we have to discretize the system in one way or another. So I will denote any discrete time by k, and the state of the system is encoded in a vector called xk. So xk is a vector that stores, okay, where I am exactly at time k. Then I take a decision or a control or an action, I mean, whatever the name, that I will denote by uk. And once I know xk and I take my decision uk, the system will evolve between time step k and time step k plus 1 with a dynamics, right? So xk plus 1 is equal to jk xk uk. So usually, the discrete dynamics is a discretization of an ODE. For instance, if you use collocation. If you want to understand everything about collocation algorithm, just go read the book by Bigler. It's actually quite well known and quite practical. One of the most basic collocation algorithm is called explicit Euler. Of course, then you have implicit Euler or the Runge-Kutta discretization. And of course, then you get more complicated collocation scheme like Hermite-Simpson and so on. But all this collocation scheme at the end, they take a continuous ordinary differential equation, and you get as output an equation like that couples the system, I mean the state at time k plus 1 with the state at time k. That's for the dynamics. So this constraint is the most important one. And then we want to work with real-world system. In the real world, you have constraints that you have to deal with. So I will suppose my system is also subject to some operational constraints that for both on the state and on the control. So now I'm ready to state my optimal control problem. So I will suppose given an initial position that I will call underline x, and I will look at minimizing the functional Lk over an horizon capital N. So I am an optimizer, so I write the problem as follows. I want to minimize, so my decision variable are x and u. X is the dependent variable, u, the control, is also called the degrees of freedom. So I want to minimize the sum of my cost plus the final cost, while being subject to the dynamics, right? Starting at the initial position. And also, I have to satisfy the operational constraints. That's what I do mean by optimal control. It's a problem with that structure. That's right in discrete time. So in what follows, I will denote by x. I will just stack all the x together from time 0 to capital N. And I will do the same for the control. It's just to simplify the notation. So here you get an optimization problem with a given structure. So you have an objective, nonlinear, a set of equality constraints, and you get some inequality constraints. So what I will do is I will describe this problem as a nonlinear program. So by introducing W equal to XU, I can say that the previous problem corresponds to minimizing a cost, F, while being subject to some equality constraints and some inequality constraints. Of course, your variable W is quite high dimensional. As you increase the horizon N, you increase the dimension of W. So NLP is not straightforward to solve, so to say. Also, this problem is nonlinear. It's also non-convex. So when you solve this problem using Newton, usually you will just get a local optimal solution. And you will hope that this local optimal solution is good enough for your purpose. It's not always the case. It's usually the case, but it's not always the case. But at least we have some good news, is actually the problem NLP is quite well known in optimization. There are a lot of optimization solvers to solve this problem NLP. These solvers are using different algorithms, so they can use augmented Lagrangian algorithm, like the solver Lancelot or Algenka. They can use SQP. SQP, it's quite well adopted in the optimal control community, way more than in the power system community, actually. So, I mean, some good SQP solvers are filter SQP or SLOT. And then, of course, you can solve this problem NLP with the interoperant method. Usually people are using IPOpt, but Nitro is also quite efficient. And of course, if you want to be cutting edge, you can use ManNLP. So ManNLP is not as good as IPOpt, but it can run on the GPU. That's the trade-off. So here we are. So now I have to describe what is the solution of this problem NLP, right? So is this problem well posed, and how can I solve it? So to do that, I have to introduce a set of stationary conditions called the Karush-Kuhn-Tucker condition. So first, I will put the problem NLP in standard form by introducing a slack variable S, which is non-negative. By introducing this slack variable, I'm just factorizing all the inequality constraints in that simple bound constraints. Usually we do that because it's much easier to find an initial feasible point with relation to the positive hortant than with relation to some complicated feasible sets that involve edge. So it's very usual in optimization to introduce a Lagrangian. So the Lagrangian is just objective plus the constraints multiplied by some dual multiplier, right? On the Karush-Kuhn-Tucker condition, write exactly like that. So if your solution W is regular, I will explain what do I mean by regular in the following slides. Then KKT gives you that there exists a dual multiplier YZ that satisfies this set of non-smooth equations. So first, they put the gradient of the Lagrangian to 0. Second, they satisfy the constraints, right? And last, you get they also satisfy a complementarity condition, which states that it's either your slack S is positive or your multiplier Z is positive. You cannot have both. So this complementarity condition is the most important condition in the Kakati stationary equation. And that's the reason why it's not trivial to solve the problem NLP. It's only because of that. Because if you remove this complementarity condition, you are just good to go with the Newton algorithm. And it's usually very easy to solve your problem. So the hard part in NLP is the inequality constraints that port on the slack variable S. If you don't have these inequality constraints, the problem gets much easier. So how do you deal with this complementarity condition? Well, it's not trivial, and we will see in the next section that to do that, we will use the interpret method. But before doing that, I have to state to determine if my problem is regular or not. Because, I mean, you can write a random objective on some random constraints, but you have to be very lucky for your problem to be regular. So you have to specify in which way your problem is well posed. Right? So that's exactly what I will do now. So to introduce the first order regularity condition, I have to introduce the following active set. So it's a set of index that puts the inequality constraint to 0. You can define equivalently the active set with the slack variable. So it's a set of index I such that the slack variable is equal to 0. It's equivalent to define the active set that way. And once you have the active set, you can define the active Jacobian at a given point W. So the active Jacobian is the Jacobian of the equality constraints plus the Jacobian of the active inequality constraints. So it's just the Jacobian of all the constraints that act as equalities. Then we say that the point W is qualified if you can describe the local geometry of your feasible set with a linearized model. So then you just have to, for instance, to use this Jacobian to describe locally how does your feasible set behave. So if you prefer to look at the math tells you that the point is regular if the tangent cone of the feasible set is exactly equal to the set of the linearized feasible direction. So if you're interested into that, I can refer to the chapter 12 in Nocedal on Right. But I'm not giving a lecture on nonlinear programming. I'm giving a lecture on optimal control. So I won't go much into the detail. So once you have that, you have some other conditions that are easier to satisfy than stating that the tangent cone is equal to the set of the linearized feasible direction. The first condition is called the linear independence constraints qualification. It's called LICQ in short. And we say that W satisfies LICQ if the active Jacobian is full row rank. And you get an alternative condition called the Mangasarian-Fromovitz constraints qualification. So usually LICQ implies MFCQ. Oh no, the other way around, sorry, I'm getting tired. So MFCQ, LICQ is stronger than MFCQ. And you say that your point satisfies MFCQ if YZ equal to 0 is a unique solution to the following linear system. So it's a linear system with inequalities. So we like the Mangasarian-Fromovitz constraints qualification in optimal control because it's quite rare to have an optimal control problem that satisfies LICQ as soon as you have state constraints. So I will explain that in 2 slides. I like MFCQ because it says, using Gobin's theorem, that if MFCQ is satisfied, then the set of optimal multipliers that satisfies the Kakati condition is bounded. Actually, it lies in a compact unbounded set. And this fact helps a lot the nonlinear solver used under the hood. because if your set of multiplier is unbounded, you get a lot of numerical issue. But usually, if you satisfy MFCQ or the stronger condition LECQ, you don't get that behavior. So of course, if you satisfy LECQ, then your set of optimal multiplier is not only bounded, it's actually a singleton. You get a unique multiplier YZ. That's for the first order condition. So all what you need to remember is you have two principal constraints qualification, which are LECQ and MFCQ. So that was for the first order condition. Now I have to detail the second order condition. So to detail the second order condition, I need to introduce this notion in nonlinear programming called a critical cone. The critical cone is defined as follows. So it depends on the sign of the multiplier associated to the inequality constraints. If this multiplier is is positive, then it states that your inequality constraints behave exactly like an equality constraint. But if this multiplier is equal to 0, and the associated constraint is also equal to 0, that means this constraint is unspecified. We cannot say it behaves like an equality constraint, because if we perturb slightly the problem, it can become an inactive constraint, or it can become an equality constraint. So we have always to treat these constraints apart. They are kind of the undecided constraints. And you say your problem satisfies strict complementarity if all your inequality constraints have a positive multiplier Z1. So you don't get any undecided constraints. In that case, it's much easier to describe the critical cone. So the most important second order condition in nonlinear programming is called SOSC. And we say that a primal dual solution satisfies SOSC if you get the following inequality. So for every direction inside the critical cone, -0, of course, you get a positive equality if you multiply on the left and on the right by D, the Hessian of the Lagrangian with relation to W. It just says that your problem is locally convex. And it says also something else, which is like W is an isolated solution. So now if you satisfy strict complementarity, you can prove that your critical cone is in fact the null space of the active Jacobian. So in that case, SOSC becomes if you satisfy both LECQ and strict complementarity, SOSC becomes equivalent to the following condition. So if you multiply on the left and on the right the Hessian of Fourier Lagrangian by Z, the basis of the null space of the Jacobian, then this matrix is positive definite. So this matrix is quite important for us because it's called the reduced Hessian. And I will explain why it's important for us in the third section of this talk. Any question? That was for the mathematical part. So are optimal control regular? Well, in fact, it's more complicated than that. So it turns out that it's not always the case. So you have actually to be careful about your first order and your second order stationary condition. For instance, if your optimal control have pure state constraints or mixed state constraints, exactly as in our setting, then you don't have enough degrees of freedom in your problem. And usually, as soon as you get active state constraints, your optimal control problem does not satisfy LECQ. Usually it satisfies MFCQ, but it does not satisfy LECQ. So that can give some issue inside IP out. The second problem is more tricky. You have to go more into the theory of optimal control. But it just says that if your problem has a singular arc, so I will show to you a singular arc in a few slides, it just it has a lot to do with linear programming, actually, but it's beyond the scope of this lecture to describe that. But let's just say that if your problem is a singular arc, then it does not satisfy SOSC. It's not strictly convex near a solution W. So a good example for that is the infamous Goddard-Rockets problem. So just to summarize, as soon as you are solving an optimal control problem, it can break LSAQ and it can break SOSC. So actually, you have to be very careful when you do optimal control. And what we observe in practice, so I think some of you are familiar with optimal power flow problem. So optimal power flow are easy compared to optimal control. And as soon as you are solving optimal control problem, you have to be very careful with what you are doing with your solver. And for instance, if you look at the convergence you get in IPOT, it's not as straightforward as what you get with optimal power flow. So IPOT is usually doing a lot of primordial regularization. It enters a lot into feasibility restoration and all that stuff. And it's really hard to solve non-trivial optimal control problem with nonlinear solvers. Mostly because of that. Most of the time, it does not satisfy LSAQ if you have state constraints. Or if you have singular arc, then you don't have SOSC. That was for optimal control and nonlinear programming. So now I would like to talk a bit more about the primordial interoperant algorithm we use inside MadNLP. So the idea behind interoperant is quite easy, actually. It just replaces the complementarity constraints in the KKT condition using a homotopy, right? So we fix a barrier parameter mu, and we replace the constraints as states that the slack S is complementarity to the dual multiplier Z. So there is a typo right there. So it's not new, it's Z. But it replaces complementarity constraints with this one, which is much easier to deal with. So as soon as you do that, as soon as you rewrite your KKT condition using homotopy, you get a smooth system of nonlinear equation. And you know that it's quite straightforward to solve a smooth nonlinear system of equation using a globalized Newton algorithm. So here you go. You get the primordial interoperant algorithm. The idea is just very easy. Is you fix a barrier parameter, you solve your system of nonlinear equation, and then you decrease your barrier parameter using a rule. So in nonlinear programming, we use either the Fiacco-McCormick rule or we use an adaptive barrier. Both are working. So it just boils down to the Newton method. So if you are familiar with Newton, it just translates to the solution of a sequence of linear systems. So at every Newton iteration, or should I say interoperant iteration, we compute the Newton state, decay, as a solution of the linear system. So we compute the Jacobian of my equation with relation to W, and I solve the following system. The right-hand side is exactly the current residual, and I factorize this Jacobian, and then I do a back solve to recover my descent direction decay. And as soon as I have this descent direction, I can update my primordial variable Vk. So Vk is I just stack W, the slack S, and the dual multiplier Y and Z together. And you just have to compute alpha k, a step alpha k using any globalization algorithm. So if you use IPOpt, you will use a filter line search algorithm. If you use Nitro, you will use a truss region. But in IPM, most of the time is spent solving this linear system. So if you detail the structure of the Jacobian, it's actually quite specific. And it has exactly this structure after a few reordering. So you observe that this matrix is sparse, so you get a lot of zero inside. And it involves the Hessian of your Lagrangian, W, in the upper left block. And you get the Jacobian of the equality constraints at the lower left, and its transpose at the upper right. And the block at the lower right is equal to 0. So this matrix is sparse and is indefinite, which gives a lot of problem in linear solver, unfortunately. So we will see how to deal with that later on. So this system is called an augmented KKT system, if I follow IPOT convention. And this is a system solved by default in IPOT to compute the descent direction. So I won't detail the right-hand side, but here the right-hand side is exactly the KKT residual. But it's not the most interesting part right there. So how do you solve this linear system? So what you want to use is a direct solver. So you will just decompose your matrix as a lower triangular times an upper triangular with a matrix in the middle. Usually the matrix in the middle is diagonal or block diagonal. So why doing that? Because of course you can use a direct solver, but you can also use an iterative solver. The problem is in the interpret method, as you drive your barrier parameter mu to 0, your system gets a condition. In fact, what we observe in practice inside IPM, it's all the iterative solver are not practical. That means we cannot use this very efficient algorithm to solve our linear system to compute the descent direction. We have to resort to a direct linear solver. And the second problem we have, so the direct linear solver are quite efficient to this days, but they require some what we call numerical pivoting to get a stable factorization. If you don't have numerical pivoting, it's much harder to solve, to get an accurate descent direction, to get an accurate solution of your linear system. And we will see in a few slides from now that if you are using numerical pivoting, then your algorithm gets very difficult to parallelize. That means these very efficient sparse linear solvers, they work very well on the CPU, but they are impossible to port on the GPUs. And it was observed before in that article by Byron Tassef on co-author. So what we use, the factorization we use in IPOT or in Nitro is the factorization implemented in MEMS or HSL. If I say HSL MA27 or HSL MA57, these are the solvers used internally in IPOT. And what they compute is a Duff-Reid factorization or a variant of this factorization. Usually, you decompose your matrix A as follows. So you do some permutation to reduce the fill-in in your linear system. And then, as soon as you have computed your fill-in reducing permutation matrix, you compute LBL. So with L, a lower triangular, B, a block diagonal matrix with block of dimension 1 to 1 or 2 times 2, and you are good to go. Except if you have only P, L, and B, your factorization is not numerically stable. So to prevent instability, people are adding an additional permutation called Q. Q is an additional pivoting that comes on top of the static pivoting P. And you have to use Q to get numerical stability inside your algorithm. So usually you compute Q on the fly. Each time you factorize your matrix, you have to recompute Q. You cannot decide in advance what will be your numerical pivoting. And this is the non-trivial part in a sparse linear solver for IPM. Usually, you can write down your own solver with static pivoting without any issue. But as soon as you have to deal with numerical pivoting, so with this matrix Q, everything gets much harder. So just to give a brief history, the LBL factorization is actually known since the 70s. For instance, you have a very good article by Fletcher that dates back from, out of my memory, 1975. But the LBL has become competitive only in the 90s, mostly because thanks to a technique known as matching-based preprocessing. So I refer to this article by Duff and Koster to detail this algorithm. On the progress in sparse linear solver, I mean, it explains a lot why IP-opt on Nitro became popular in the 2000s. Without the LBL factorization, you cannot have IP-opt on Nitro. I mean, this nonlinear solver, they are too reliant on the sparse linear solver to be tractable if you don't have an efficient implementation of the Duff-Reid factorization. That was for the linear algebra part. So now I just have to introduce a few more notions before explaining how to run everything on the GPU. So what we can do is we can exploit the structure of the augmented KKT system. And you can remove the block associated to the inequality constraints to get the following condensed KKT system, which is smaller than the augmented KKT system, but it has some additional fill-in, so it's not as sparse as the original augmented KKT system. And it's usually useful only when you get a large number of inequality constraints, or if you have a GPUs. I will explain that later. So we will deal a lot with the condensed KKT system in the next session that detail how we have implemented MonNLP on the GPU. But the good thing is, if you look at this condensed KKT system, in fact, it has some very nice interpretation in terms of optimal control. So I will just recall that basic fact. So if your matrix K is positive definite, which is not always the case, of course, but let's suppose it is, then the solution of the saddle point linear system. So suppose that here you get the condensed KKT system we were dealing with in the slides before. Then the solution of this saddle point linear system is exactly the primal dual solution of the following convex QP. So suppose now we have an optimal control problem with a set of state and a set of control that are coupled with a time dynamics. And if you look at the condensed KKT system you obtain after discretizing your nonlinear problem and passing it to IP-opt, to any IPM solver. And if you look at the structure of the condensed KKT system you get as output, then it has exactly the following structure. It has the QP you are solving when you solve the condensed KKT system. It has exactly a linear quadratic regulator structure. That means you can solve this linear system. Instead of using a sparse linear solver, you can solve a convex QP with a very specific structure, with a LQR structure. And I think you know how to solve the LQR. You know that you can solve the LQR with backward recursion, which are quite efficient in practice, if your problem is not too large, of course. Of course, to do that, you have to assume that your matrix K is positive definite. So it's not always the case in nonlinear programming or in nonlinear optimal control. So you have to convexify it beforehand, before solving the LQR. So I recommend reading the following article by Verschuren, Zanan, Kirinen, and Dill, which present how to convexify the problem to get a well-posed LQR inside your iteration. You can also have a look at this very interesting article by Dun and Bertsekas. Here they explain the link between that system and the infamous LQR problem. Okay, so what we get so far is we have introduced the interoperant method. We have seen that the interoperant method just translates to the solution of a sequence of linear systems that are sparse and definite. But you can condense this linear system down to a condensed KKT system which for optimal control exactly encodes a IQR problem. And we will see in the next section how to use a condensed Kakkati system to solve the linear system entirely on the GPU. But before doing that, I want to have a word of caution. I like the IPM. I'm a big fan of IPM. I mean, I'm spending all my life developing IPM solver. But we have to emphasize that the IPM solution is not always accurate, on the contrary to active set solver, like SQP. So I don't know if you know the Godard rocket problem. It's just a minimum time algorithm. So you have a rocket that has to change its orbit between, it has to reach the maximum orbit it can reach at minimum time. And it's known that the Godard rocket problem has a singular arc. Actually, this poses a lot of problems for IPM. So I just take the Godard problem, I solve it with IPOpt at a given tolerance. So here is the solution I get. So this is the thrust against the time. The thrust is like the amount of energy you put in your motor, more or less. I mean, the amount of fuel you are consuming in your motor. Here is the solution I get if I set my tolerance to 10 minus 4. So now I will decrease my tolerance. So you can see that if you decrease your tolerance by a factor of 100, the solution gets very different from what you had before. And as you decrease the tolerance further, you get this oscillation that comes in your solution. And they don't disappear if you decrease your tolerance. So this is caused by the singular arc in the optimal control problem here, because it's known that the Godard rocket problem has actually a singular arc. And the solution returned by IPM, it's slightly inaccurate. I mean, these oscillations are not realistic. So usually, you have to use a crossover on top of your IPM solution to recover an accurate solution. So here, this is a solution I get with a discretization being equal to 100. So what happens if I increase the discretization to 1000? I get exactly the same phenomenon. So of course, the solution is more accurate, as you can see. So here you get like a bang-bang solution here and here. And here you get the singular arc. So of course, it's more accurate. You also take more time solving the problem in IPOpt, but you still have this oscillation, for example. So you still have to use a crossover to recover the original solution of the Godard rocket problem. So please be careful with that. Every time you use an IPM solver, be careful with the solution you get. And remind that the IPM solution is always inaccurate. That's the message I would like to pass in that part of the topic. So now we are ready. We know IPM. I mean, you know how it works now. You know that it has some plus and it has also some downsides in terms of accuracy. But let's keep it as it is. And let's explain how we can run the IPM on the GPU. So before going into that section, I would like to know if there are any questions from the audience.
Yes.
So,
can we see if we got everything to this point? The message that you were trying to say, right? So you started presenting our interior point method or the optimal control approach, and how we solve that with IPM normally, and then how many times we use this relaxation. We're using the mu to kind of like smooth things out and get that solution.
Exactly.
And of course, there are a few problems there, and it's hard to parallelize everything. And then you did present the approaches. You presented first the augmented KKT system to then present the after the condensed version, right? And then in the middle, you present doof rate factorization.
Yes.
I got a bit lost. From what I understood, the doof rate factorization was a way to kind of condensify or avoid some of the problems with the ill conditioning of the previous factorizations approaches, right?
Kind of. Also because the system is indefinite.
Mm.
It's sparse indefinite. That's the reason why it's much harder to solve than a positive definite system. If your system is positive definite, then you can use Cholesky. And Cholesky is numerically stable.
And if it's not, then you can use the doof rate factorization
Yes.
to kind of try to get around that. And then, but then you jumped to the condensed KKT, and that's a different thing, right? Like that's a different way to approach the problem.
So indeed, let's come back to the condensed KKT. The condensed KKT is almost equivalent to the augmented KKT system. I mean, it's not equivalent. I mean, the solution is the same, but it's still sparse indefinite because you have a 0 in the lower right block. So that means that if you want to solve your condensed KKT system with a linear solver, you should also use the Duff-Reid factorization.
See.
Except if you have an optimal control problem, and in that case, you may want to solve it using LQR. I think there is an interesting connection between the condensed KKT system and the LQR, which is often overlooked. That's the reason why I have these slides, for example.
So it's not always the case when you can write it in the condensed KKT way that you can solve with LTR. Because I know that LTR is not always the case.
Only for optimal control.
Only for optimal control. So what's the... Okay, I see. Okay. So in the case for the condensed interpretation that you can write it as a QP, what are the specific conditions that you need for you to be like? I'm trying to figure out what is the catch, right? Like what does my optimal control problem has to have for it no longer to be able to be modeled in the way that we could solve with LKR?
If you have a dynamic structure, and if you split your decision variable into a control and a state, it's very likely that you can write the solution of your condensed KKT system as a LQR.
So if I had like general constraints on the state, I could just rewrite it in, because LQR normally means that you don't have the constraints, but yes, of course I can add slacks, right?
But we use IPM, right? And then we have removed the inequality constraints from the linear system to get the condensed KKT system. So the inequality, they appear in the linear system only in the matrix K, right? And here you get only the Jacobian of the equality constraints. It's like, you know, we can interpret the IPM with a log barrier. So suppose we take the original problem, optimal control with inequality constraints. You move all your inequality constraints in the objective using a log barrier. Then you linearize it with Taylor at the order 2. You get exactly the same linear system. I don't know if I'm clear. Sorry about that.
No. What you're saying is maybe I'm not posing my question appropriately. I'm trying to figure out what is the specific structure on the control problem that is not present in the general optimization problem, so that we could rewrite in this way, right? Because the system there appears very similar to the previous one, right?
So what we have is a dynamic structure.
Is it the block diagonal that you get from the dynamics?
Yes, exactly.
I see.
It's just that.
I see. I see.
What is an optimal control problem? It's a set of very small problems that are connected together with a loose dynamics. The coupling between two sub-problems is very loose. You just have this dynamics coupling. That's the reason why it has a very specific structure.
So if I had varying dynamics throughout my time horizon, then that would break that structure, right?
Yes.
Fair point.
If
Thank
you
you.
connect
Sorry.
every time step with each other, you just break everything.
That
But
makes sense.
here, the optimal control is just say that you only couple time k with time k plus 1. It's not connected to time k plus 2, k plus 3, and so on.
I see. So just going back and just connecting with the final things you presented after that, you're saying it would be great if we could model this way. If we cannot, then we go back to IPM, and then now, but you have to be careful with the issues that you have with the precision there, right?
So you will have this every time you use IPM.
Perfect.
So
Thank
if you solve your original optimal control problem with inequality constraints with IPM, what I just said is you just have to solve a sequence of LQR problem. But you will get the same solution as with a sparse linear solver. That's what I mean by LQR. It's just a way to replace your linear solver if you have a problem with an optimal control structure.
Yeah, one of the methods that we saw was what they call it differentiable dynamic programming, that keeps kind of like creating LQR, solving it, and using to kind of like find a new nominal trajectory, right? So that would be very similar to like that we're bridging to what you did there, right?
Exactly. You nailed it, Andrew. It's exactly that.
Perfect. Thank you.
But I think it's very important to make that connection. So I know it's slightly confusing, but it's something very important to understand.
Perfect.
So I actually had some questions on sort of the same slides.
Okay.
Do you do how the stages are coupled using just equality constraints? Like if you had block diagonal, but with inequalities, you wouldn't be able to do that kind of substitution.
Block diagonal, but with inequalities?
Yeah, so it comes from the fact that you have xk plus 1 equals a function of xk.
Yes.
So if you had joint constraints on xk and xk plus 1, but they were inequalities,
yes. It breaks.
If you found the movement between them or
It
something, that would
breaks.
break it.
The inequality constraint have to stay local.
And then, so the other question I had here was to do with the term fill-in. So I've seen it a few times now, and I usually just ignore it. But I figured maybe you have some good explanation for what that means, why it's relevant.
What's the term you said?
Fill-in.
Fill-in. So it's just, so you decompose your matrix with a lower triangular times the upper triangular. So here it's just a LU factorization. It's not a LBL. So the amount of fill-in is, if you look at the matrix L, and you look at the rows of this matrix. So the amount of fill-in is the number of non-zero, the maximum number of non-zero you can get on a single row. Right. So here you observe that the fill-in is higher for these rows than for the original rows, right there. And the more non-zero you get on this line, the harder it gets to perform the backsolve.
Oh, so it's not just about storage, it's about the speed of the backsolve also.
It's both. Here, if you get dense rows, you just break up, you can break up the memory of your linear solver. But it gets much harder to do the backsolve.
And then I had another question about singular arc. What does that mean?
Yes. So it's hard to talk about singular arcs, but just how to say that simply. So I like to come back to the Godard problem. So if you look at the accurate solution you get, I mean, more or less accurate, up to IPM tolerance, accurate solution. So what you may know is most of the time, the solution of an optimal control problem is bang bang. It's like when you do linear programming, right? Your solution is at the vertex of your polyhedron. So in classical optimal control, your polyhedron is just a box. You just have box constraints. So of course, in that case, your solution is bang bang in the sense that it's either your control is set to the max or it's set to the min. Okay, there is no in between. So that was the original observation. Then came the singular arc problem. The singular arc problem is what happens when your solution is not bang bang. Right? It's a solution which is not set at the max or at the min.
I guess that's due to the objective being non-convex.
And the objective is not necessarily quadratic. I know it's a bit tricky to explain without all the math. But it has, if you have to introduce a singular arc properly, you have to introduce the Hamiltonian and to do some continuous time dynamics. And I didn't want to do that in that lecture.
I think I get what you mean, though. It's when you have an objective that's more complicated, and so you can't like assume that you're going to be at the boundary of the feasible region. Is that fair?
It's you see, for instance, if you have QP, and your matrix Q in your QP is semi-definite. I mean, what it says, you have a singular arc when your reduced Hessian is not positive definite. I know it's not that obvious, I'm sorry about that. But the intuition is exactly that. It's hard to prove in that case that your solution is. It's hard to prove that your solution is isolated with just a second order model of your nonlinear dynamics.
I'll definitely look into it a little more, but I think I get what you mean.
I'm trying to do the intuition, but I know it can be confusing.
Can I add one? Yeah, go ahead. Sorry.
Sure, please do, Andrew.
You mentioned the Hamiltonian, and that got me thinking about the issues that happened with the like shooting methods, right? Like that they try to kind of like compute the solution and then they go back updating, yes. Right? And a lot of times people said that U conditioning there happens exactly for the same reason that you talked about, and they kind of motivate that to use IPM methods or other types of methods that are not these shooting methods. It's funny to see that these cause issues as well in IPM, for example, right?
Yes, it's exactly the same problem. If you use the shooting method and you have a singular arc, you have to regulate. I mean, actually, the shooting method is a kind of Newton algorithm. And when you look at the Jacobian you compute in the shooting method, you have to regularize it because it's singular. It gets singular as you approach optimality. And of course, there is no free lunch, so you will get the same issue with IPM. And actually, we have the same issue with IPM. Singular arc are a mess.
More questions before François moves to the next session?
Can you please briefly explain again how you derived the condensed KKT?
Sure. So let's move back to the augmented KKT system. So you get the following system. You observe that it's very easy to remove the update with relation to the slack because it's equal to sigma s ds times plus dz is equal to minus R2. So you can just directly derive dz is equal to minus R2 minus sigma S ds. Okay.
Yeah.
Then you replace, you also have that ds is equal to the Jacobian of h times dw minus R4. And you just have to replace everything in the first line.
In the
And you
first
get
line.
exactly that equation.
Oh, okay.
It's just very basic linear algebra.
Okay.
You're just pivoting beforehand, right? Like you're just pivoting. You're just pivoting with respect to some
Yes.
dimension.
And I am doing the pivoting explicitly. But it's exactly some kind of manual pivoting. Okay,
I think we can move to the next session.
excellent. So GPUs, what can we get out of GPUs? So why is it difficult? For a lot of reasons. So just off the record, I started my postdoc in 2020, and it took us like 3 years to get something working on the GPUs. So it was non-trivial, that's for sure. And at the end, what saved us is the release of NVIDIA's UDSS, which was just a very good sparse linear solver finally available on the GPU. The problem is, if you look at what algorithm you have in NVIDIA's UDSS, you don't have the Duff-Reid factorization. That means you cannot solve the condensed KKT system or the augmented KKT system with UDSS. It just breaks. I mean, you can try, but it will break. It will break anyway. So you have to use a few tricks in linear algebra to use NVIDIA's UDSS, but it's well worth it because as soon as you have used this trick, you can rely on this very efficient linear solver and everything gets so fast. So I will exactly detail that in that section. So first, I will just briefly discuss how to reformulate the KKT system as a dense matrix. And it corresponds more or less to the reduced space approach in nonlinear programming. And in the second part, which will take more time, I will detail the full space approach where we use a pivoting free factorization. By that, I mean Cholesky or sign Cholesky, all implemented inside NVIDIA's UDSS to compute the solution of my KKT system. So the first method is actually quite well known since the 80s. I mean, before having efficient sparse linear solver, all the optimization people were using the reduced space approach in one way or another. So it was quite used in the 70s or in the 80s. It's in optimal control, it's also called the few degrees of freedom approach. And actually, the idea is quite simple. So if you look at the previous condensed KKT system, you can exploit the structure of the KKT system further if your Jacobian is full rank. That means if you have LECQ. Then if you denote by Z a matrix whose columns are a basis of the Jacobian, of the null space of the Jacobian. So that is Z a matrix with a full rank so that the Jacobian times Z is equal to 0. Then you can prove that your condensed KKT system that we have shown before is exactly equivalent to that system. So you multiply on the left by Z transpose your block, I mean your condensed matrix, which appears in the upper left block in your condensed KKT system. You multiply the same matrix by Z, and you get the following system. And you get only the direction with relation to the degrees of freedom. And you get a right-hand side, which is quite complicated, but I won't detail the right-hand side right there. So that means that if you can compute the matrix Z efficiently, which is the case, for instance, in optimal control, and you have not that many degrees of freedom, you just have to compute that matrix, which most of the time is dense, factorize it using dense linear algebra. And we all know that dense linear algebra is quite efficient on the GPU. And then you solve this system and you recover the solution of your condensed KKT system. So you have a bit too many assumptions. So because we suppose the Jacobian is full rank, as we have seen before, it's not the case. It's not always the case in optimal control. And you have to suppose that you don't have that many control, right? Otherwise, you get a dense matrix which is just too big. So you will just blow out your memory. But I will just give an example of null space for optimal control. So if you can decompose your Jacobian as that, so you separate the Jacobian with relation to the state and the Jacobian with relation to the U, to the control U, and your matrix Gx is invertible, then you can compute the matrix Z exactly as follows. You can verify by hand that if you multiply this matrix on the right by Z, you get exactly 0. Okay. So this is a trick which is actually good to know because it's quite used in PDE constraints optimization. Because in that particular case, you have a lot of dependent variable, X, and you have very few control. So X can be like, you can have like 10,000s, hundreds of thousands, or millions of variable X, and only 1,000 of control U. So in that case, you have to use this trick to get a tractable solution. And it's worth it because at the end, the matrix you get is quite small. That was actually our first approach to solve large-scale nonlinear program on the GPUs. We were using this null space solver. The problem is what happens if you have many control, then it just breaks because your dense matrix Z transpose KZ is just too big for your GPU's memory. So we had to give up, unfortunately. This approach was not that fruitful for optimal power flow or optimal control. So instead, we switched back to the previous full space approach, which is also called the many degrees of freedom approach in optimal control. And we thought a lot on, okay, so we won't have a Dufrid factorization on the GPUs. It's just too difficult to implement that. But what if, instead of using the Dufrid factorization, we reformulate the KKT system to use a pivoting-free factorization, like Cholesky. That means that as you don't have to compute numerical pivoting, you just have to rely on your static pivoting, and your algorithm gets much easier to parallelize. I mean, as soon as you remove this matrix Q in the Dufrid factorization, everything parallelizes very, very smoothly. So we thought a lot on how to do that, how to avoid the numerical pivoting of the Dufrid factorization. So to do that, there are not that many ways. You have actually two paths you can take. Is either you reformulate your KKT system as a positive definite system, or as a symmetric quasi-definite system. So a symmetric quasi-definite system is a system where B is full rank, and the matrix A and C that appear on the upper left and the lower right are both positive definite. So you know that you can factorize a positive definite system with Cholesky. You can have a look at Golub, for instance, to have the proof of that fact. And the good news is if your matrix is symmetric quasi-definite, actually you can factorize it using the signed Cholesky factorization. We just introduce a diagonal matrix between the lower triangular and the transpose of the lower triangular. And you are good to go. So how to do that? How to transform your KKT system down to a positive definite system or a symmetric quasi-definite system? That's exactly what takes us 3 years to figure out. So we just look back at the condensed KKT system we had before, which again is sparse symmetric indefinite. So how can you reduce this system down to a positive definite system or a symmetric quasi-definite system? So actually, we found that there are three strategies to do that. The first one is called lifted KKT. The second one is called IKKT. And the last one is called NCL. And it's equivalent to an augmented Lagrangian algorithm. So lifted KKT is actually quite easy. The idea is, okay, if you look at the structure of the condensed KKT system, what is the issue? The issue is it's indefinite because that block is equal to 0. But if you don't have any equality constraints, you just keep this matrix K, which most of the time in nonlinear programming, once you are close to convergence, is positive definite. So the idea is just to remove all the equality from your problem. So you will fix the relaxation parameter tau, positive, and you will solve a relaxed problem with only inequalities. You reformulate your problem with slack variables, and you use the same condensation strategy. And at the end, the condensed KKT system you get with this relaxed problem is exactly that one. If you look at the left-hand side, you get only this matrix K2, which is equal to, so here is a typo, it's K2, is equal to W plus the Jacobian of your constraints times this diagonal matrix times the Jacobian of your constraints. And the good news is this matrix is close to a positive definite matrix once you approach convergence. Or if it's not, you can just add a multiple of the identity on the diagonal to get a positive definite system. So that's exactly what we do. We relax the problem, and we solve the condensed KKT system associated to the relaxed problem, which is, after using a regularization, a positive definite matrix, which can be solved with Cholesky. That was the first trick, or the first strategy. Then you can also use a second strategy, which is exact. Exact in the sense that it tackles the original problem. And it's also known as the Golub and Griff method. It has been known since the 2000s, I would say 2003. And the idea is to reformulate your condensed KKT system using an augmented Lagrangian reformulation. So you can prove that the condensed KKT system is exactly equivalent to that system. You just have to multiply by gamma the Jacobian, so the first line, and to sum up the first block with the second line of blocks. So the condensed KKT system is this time exactly equivalent to that system. And you know from the theory of nonlinear programming that if gamma is chosen large enough, then the matrix K gamma is positive definite. That is, you just have to increase gamma till this matrix is positive definite. And you can solve the condensed KKT system by solving this following set of equations. Right, so this is the normal equation associated to that system. Here you just reduce the first block of lines, and you just consider the last block of lines with relation to the update with relation to the multiplier. So here you observe that you have the inverse of K gamma that appears in your left-hand side. So of course you don't want to evaluate the inverse of K gamma right there. So what you're gonna do is you will just solve this linear system with a conjugate gradient algorithm to avoid explicitly evaluating this inverse right there. And it turns out that if you choose gamma large enough, I mean, by large enough, I mean to a very large value, like 10 to the power of 7, 10 to the power of 8, then the conjugate gradient algorithm will converge only in a few iterations, like less than 10. So actually, it's quite efficient to solve the normal equation with CG. Even if your matrix is ill-conditioned, gamma is so large that all the eigenvalues in that linear system clustered around 1 over gamma. And you know that if you don't have many different eigenvalues in your system, that the conjugate gradient will converge very efficiently. That's exactly what we are right there. We are like in an optimal case for the conjugate gradient algorithm. And we are good to go. What we have to do is we just evaluate K-gamma. We factorize K-gamma using Cholesky, and we solve the remaining normal equation using a conjugate gradient algorithm. So we have to do as many back solves as we have conjugate gradient iteration, but it's usually very efficient because we converge in only 10 conjugate gradient iteration. So usually lifted KKT is much faster than IKKT, but IKKT is more accurate. That's what we found out. And why IKKT is more accurate is because it's solving exactly the same linear system as the classical IPM method. We don't have to reformulate the problem using an equality relaxation strategy. The problem is how to choose gamma. So if you look closely at the original paper by Golub and Griff, they say that their method is equivalent to an augmented Lagrangian method. And actually, it's true. So what we did is we proposed another method based on an augmented Lagrangian method. The idea is to reformulate your problem with an augmented Lagrangian penalty. So if you denote by YE the estimate of the multiplier, and if you denote by rho k the augmented Lagrangian penalty, you will solve this problem using IPM. You get a solution, you look at the primal and the dual infeasibility, and you update the multiplier estimate and the penalty rho k, depending on your current feasibility. And you just do a few iterations like that till you get convergence. So NCL is usually more robust, but it converges in more iterations than IPM, because instead of solving 1 time the problem, you are solving it like 2 to 5 times. So, but it's worth it, because if you look at the KKT system we got when we solved NCLK with IPM, they have all the good properties. So that's what we proved recently in this article, which was put on arXiv like 2 weeks ago. So we presented an implementation of the augmented Lagrangian algorithm on the GPU to solve large-scale degenerate nonlinear programs. And the idea is, if you look at the structure of your system, so here it's not the condensed KKT system, but it's the original augmented KKT system, you can prove it has exactly the following structure. That is, your block here is not equal to 0. On the contrary to what we get with IPM. You get this small term on the lower right. That means that if that block is positive definite, this system, what called K2R in that article, is exactly SQD. But W is positive definite only if your original problem is convex, which is not the case. So what happens if your problem is non-convex as in optimal control? So what we will do is we will just solve K2R not with Cholesky, but with a signed Cholesky algorithm. So the signed Cholesky is also called the LDL factorization, with a pivot regularization strategy. So every time we encounter a small pivot in the factorization, we will replace it by a small value, like 10 to minus 10 or 10 to minus 8. As a result, we will get the factorization of a perturbed matrix, which is hopefully close to the original one. And actually, you can prove it's close to the original one. And as soon as you get the factorization of this perturbed matrix, you can recover the original descent direction by using some iterative refinement strategy. E.g. using GMRS, and you can interpret the factorization of this perturbed matrix as a preconditional. So I won't go much into the detail, but just to say this is the last practical method, which is also exact. And you can interpret this parameter 1 over rho k as the gamma parameter we had before in IKKT. that's how you can solve your nonlinear problem on the GPU. You take your condensed KKT system and you reformulate it in a way you get a positive definite system. To do that, it's either you use lifted KKT, so you use an equality relaxation strategy, or you reformulate your system à la Goleman-Grif. And you just factorize this matrix K gamma. The alternative is to use an augmented Lagrangian. And the augmented Lagrangian, thanks to this property proven by Rockefeller, adds a dual regularization in the dual. And by that, I mean we add a positive term in the lower right block of your system. And automatically, that means you can solve your system using the LDL factorization, which works well on the GPU. So it was quite brief. I gave a lot of information. I hope I'm not sure it's clear for everyone, but feel free to ask if you have any question. I highly recommend having a look at this article by Goleman-Grif. You have a lot of detail in that article.
Yeah, I think we have to dive into a little bit on the math to kind of like convince ourselves of a few of the the statements. But yeah, does anyone have a specific question? How to do that?
Maybe as a summary, is it fair to say that GPUs are dense linear algebra or pivoting free algorithms? So either one or the other.
At the moment, it's mostly, I mean, we use second order method. So in second order method, all the bread and butter is linear algebra.
Saying
if
like
you use the first order method, then it's a different story because you don't use any linear solver. You just use sparse matrix vector product. And in that case, you have to work a lot more on the algorithm.
so if you're doing something that involves linear solves, then if you want to be able to get speed up on the GPU, they have to either be dense and so relatively small, or you have to use pivoting free methods, which means you have to use the factorizations you discussed.
Yes.
And is MadNLP does exactly the NCL, right?
MadNLP, good question. I should have clarified this in my slides. So MadNLP implement lifted KKT. So iKKT it should be in that repo. It's an extension of MadNLP. It's available right there. So it's not by default in MadNLP, but it's an extension. Oh, sorry, I'm not sharing all my screen. Let me put the link into the chat.
Share with the students.
And last, NCL is not implemented in MadNLP, but in a new package called MadNCL. So
I was kind of surprised when you were going over NCL, you said it only needs like under 10 iterations. I guess outer iterations is what you're talking about.
yes, 100. Can you repeat your question, Miguel?
It only needs like 10 iterations of the
Yes, outer
hierarchy.
iteration.
And are you warm starting the inner iteration somehow?
So what we usually report is the inner iteration, because that's exactly what we can compare with MadNLP. So what we observe is, in practice, you multiply the number of iterations by a factor of 3.
I see.
So,
Are you starting any, like when you go from the first iteration of NCL to the second one, are you making a new solver altogether, or are you reusing the factorization?
No, we reuse everything.
Nice, okay.
That's the only way you can get tractable.
Yeah.
So you can have a look at the implementation we have in MadenCL. I would be very happy to, if you want more detail, to answer to your question, either by email or anything.
Yeah, I'm definitely going to take a look.
So what I would suggest now is I conclude my lecture by giving some result because I think now it has been pretty dense. I gave a lot of theory on linear algebra. So let's relax a little bit. So is it worth to do all that? I think I do hope I convince you it's worth it. But if you are not yet convinced, let me give you some numerical results. So first, let's have a brief overview of the current state of the art for GPU accelerated optimization. So here is a non-exhaustive list of GPU accelerated solver. So if you look at what's happening in social network or in the press, most of the people are focusing on first order method. So in particular, CU-PDLP got a lot of attention in the recent year, for good reason, I think. Because CU-PDLP is one of the first alternatives to the simplex or the interrupt method for years. And it's actually quite efficient to solve LP problems. Not all LP problems, but if your problem is out of scale, then you should definitely use CU-PDLP to solve it. So OSQP is also solving the solution of problem on the GPU, of QP problem on the GPU. And right now, people are working a lot on making SDP, so semi-definite programming, work on the GPU using a trick called the Burrer-Montero-Laurent factorization, which simplifies a lot the solution. And you get these two recent solvers for SDP called QALAR and QLORAD. So if you look at what we have for second order method, so we have this solver developed by Brandon Amos called QPTH, which has been developed, long time ago, which is impressive. It has been developed, I think, in 2017, but it's dense. So you cannot solve any large scale problem with it. And I think right now, one of the best solvers on the GPUs is CU-Clarabel, which is support all the conic formulation you want. So here comes MathSuite. So MathSuite is the suite of optimization solver we are currently developing with Alexis and Songo. Feel free to have a look at this website if you want to have more detail about MathSuite. In MathSuite, you can find examodels, which is an equivalent of JUMP working on the GPU. And you have MadenLP, the NLP solver I described so far. MadenCL, the variant of MadenLP that implements the NCL algorithm I just showed to you, actually. And it's mostly used to solve degenerate NLP problem. And we have this more recent solver called MadIPM. And MadIPM is just an implementation of the IPM method to solve large-scale LP problem. That's more or less all the optimization solver I know that work on the GPU. And it turns out that if you look instead at what we have in optimal control, the landscape is quite different. So you don't have that many solvers that support GPU acceleration. So it's coming because all the people in robotics are all working into that now. And if you look at all the state-of-the-art solvers, they all exploit the problem dynamical structure. By that, I mean they reformulate the KKT system exactly as I showed to you before. They reformulate it using this bounded structure, and they solve it using LQR or something like that. So you have some solvers that are based on differential dynamic programming, like Altro or ProxDP. Some others are based on some condensation strategy, more or less equivalent to what I showed to you before, like HPIPM. Or some others are based on Riccati recursion on LQR, like FatTrop. And if you look at all these solvers, they are made for embedded system. And they exploit very efficient libraries. They can generate code for embedded system. It's actually quite impressive what they have developed. But the problem is, it's too tailored for the CPU, and it's very hard to implement everything on the GPUs. So most of the people have to start from scratch to develop new solver for optimal control on the GPU. So is it worth it to solve optimal control on the GPU? So what we did is we took ModNLP on CUDSS without exploiting the dynamic structure of the problem. We let CUDSS figure out the elimination tree by himself. So the idea behind ExaModel is to specify the structure of your problem in a very structured way, actually. So what we call the SIMD abstraction. So what we do is we describe the problem using a set of iterators. So we isolate all the repeated structure in the problem, and then we condense them to define an objective on the set of constraints. That means the solver knows, the modelers, ExaModels, knows exactly the repeated structure, and he can evaluate all of them very efficiently in parallel on the GPU or on the CPU. And it exploits CD parallelism to do that. So actually, it's very good for optimal control, because in optimal control, if you remember the problem I showed to you at the very beginning of this lecture, you do have a lot of repeated structure. At every time step, you repeat the same dynamics. At every time step, you repeat the same constraints. At every time step, you repeat the same cost. That means ExaModel, it's an ideal case for ExaModels. And ExaModels is super fast at evaluating an optimal control problem, much faster than Jump. So first, we managed to deliver with ExaModels. ExaModels, it just kills it. You get very fast evaluation of your optimal control problem. So here is just a benchmark that look at different optimal control problem or problem with a dynamic structure. So the Godard rocket problem, robot is another optimal control problem, which is not degenerate. And Pinel is a system identification problem. And Dirichlet is a PD constraints problem. In blue, you have the performance obtained by Jump. In orange, you have the performance obtained by Ample, another modeler. In green, the performance of ExaModel on the CPU, and in red, the performance of ExaModel on the GPU. And everything is log scale, right? So what we do is we increase the discretization of the problem. So the higher, the more accurate is the solution. And we look at the evaluation time to evaluate the full model. So mostly the Jacobian plus the Hessian. And we usually observe the same pattern. Is ExaModel, even on the CPU, is much faster than Ample or Jump. And if you evaluate the model on the GPU, if your problem is not large enough, it's just not worth it. But if you increase the discretization size, for instance, if you reach a discretization being equal to 10,000, then you get 10 times faster than ExaModels running on the CPU. It just kills it. We have the same pattern, for instance, for the robot instance. Same things for Pinel. Except for Pinel, actually, Jump is faster than Ample, which was not expected, but such is life. So Dirichlet is a PD constraints problem, so that means the problem is huge. You can look at the discretization size, it's much smaller than the others. And here, even for a small discretization, ExaModel on the GPU is faster than ExaModels running on the CPU. So all that to say that if you use ExaModel, the time to evaluate the model get negligible. Like we take less than 1 milliseconds to evaluate all the model. That means that at every iteration, we take less than 1 milliseconds to evaluate all the derivatives in our model, which is impressive, right? Because, for instance, if you look at what we get, if we have like 50,000 discretization time step, Jump takes more than 20 seconds to evaluate all the derivatives per iteration. So it's just not worth it. That means you will spend all the remaining time in the linear algebra. And the linear algebra is becoming the real bottleneck for optimal control, because examodel just kills it in terms of the evolution of the model. So that's the second experiment we did in the paper we submitted to the CDC 2 years ago. Is we look at the distillation column instance from Bigler, and we did the same experiment. We look at the time per iteration in second, and we increase the discretization size, exactly as before. In blue, you have the time per iteration on the CPU using examodels on MA27 or ME57. And in red, you have the time per iteration using CUDSS. And it's either you use lifted KKT or IKKT. So what we observe is we get much faster by running on the GPU. So for instance, for a discretization size being equal to 10,000, the running time per iteration decreases from, let's say, 2 seconds to 50 milliseconds, right? So it's almost a 10 times speed up to run your problem on the GPU. On that, without exploiting the structure, the optimal control structure. So we believe we can do even better than that. So of course, we use some expensive GPUs. The second message is we are not doing machine learning. We are not training transformers. So we don't do a lot of dense operation on the GPUs. That means we don't need a very high throughput in our GPUs. And if you look at the performance depending on the GPUs, you don't have to buy very expensive GPUs to get fast performance with examodel and CUDSS, because usually your problem is super sparse and it's just not worth it to use a super expensive GPUs because the throughput is not that large. So here is the time to solve a large-scale optimal power flow instance. So it's not an optimal control problem, but the message is more or less the same for optimal control. In black, you have the total time to solve the problem on a MacBook Pro. So it's like 2 minutes. If you solve the problem using a H100, so a state-of-the-art GPUs, your solution time gets less than 10 seconds. Okay. And the solution time is slightly higher if you use the previous generation of GPUs. So for instance, if you use the A100. But if you use a commercial GPUs, for people like us who plays video game, if you just use the RTX Pro 6000, you're actually faster than the H100. So, the H100 is, I don't know, I think it costs like 20K, 30K now. So, but it's just not worth it to buy it. You just have to buy a RTX 6000, which is also quite expensive, but less expensive than the H100. I think that's an important message to get because, these GPUs are very expensive these days. So time to conclude. I will just finish with that slide, just to say that actually it's a good wrap up with what you discussed before, Andrew. What we need is just a block 3-diagonal system. So in fact, the optimal control problem is a particular instance of a block 3-diagonal system. So right now we are trying to exploit this block 3-diagonal structure to get faster solution on the GPUs. So to that, you have two different ways. It's either you use an algorithm called parallel cycling reduction, or PCR, or you use partition dynamic programming. So if you are interested into that topic, I refer to that recent article by Jean Montoison and Chin, who just explained how to solve that system on the GPUs, which is actually very interesting. time to conclude after this long lecture. So I hope I have convinced you that GPUs are useful for optimal control. If you are interested into exam models on NoNLP, I advise you to have a look at this tutorial. So this is for optimal power flow, but everything works exactly the same for optimal control. I can actually give you a notebook that shows how to solve a large-scale optimal control problem with NoNLP on CUDSS. Feel free to interact. I mean, we are available on GitHub. You have my email. You know you have my personal website, and I will be happy to discuss all that further with you. So if you have any question, I will be happy to try to clarify some point.
Perfect. Let's thank our speaker. Thank you very much, Francois. That was a very incredible lecture, and I think very timely for the space that we are right now, right? And state-of-the-art stuff, and connects a lot of the stuff that we saw for optimal control together with hardware and how to make our algorithms appropriate for the hardware that we're currently using. So yeah, thank you very much for this. And does anyone have a question?
I have a question, but it's slightly a bit unrelated. I'm wondering if any of these kind of like GPU-based LP solvers will translate to kind of more integer or like MILT methods as like primal heuristics or anything. Are you looking into that?
That's a tough question. So that's a $1 billion question. We are looking into that. We are not making a lot of progress because it's hard. IPM is not good at warm starting, and you need good warm start to run the branch and bound algorithm you need for integer variable. So right now we are a bit stuck because of that, and we need the solution. So what we want is to have a good crossover for IPM. That means a crossover is just a method that takes the IPM solution and find exactly the active set. And once you know exactly the active set, it's very easy to do the branch and bound algorithm. So I'm also working a lot on another way to look at things. So you cannot always do that, but actually in optimal control, you can, most of the time, you can reformulate your binary variable with complementarity constraints. So it's another way to encode your logical condition. And it's actually much easier to handle because you can solve a problem with complementarity constraints with Newton. So we can reuse everything I just described in this lecture to solve the problem. But you cannot always do that. For instance, if you look at the unit commitment problem, you cannot reformulate it using complementarity constraints. So we have to deal with binary variable at some point or whatever. I think it's an open question. I believe, it's just personal opinion, so feel free to disagree. I believe the branch and bound algorithm is not the solution on the GPUs. We need something different.
Thank you.
Yeah, I have a question. You show these big speedups per evaluation, right? And also per iteration. Does this translate directly into the same kind of savings for solving the whole instance? And I'm also very curious to hear if there's any other trade-offs like the precision or the quality of the solution compared to the state of the art that you see right now.
Good question. So the speedup translate. So if you look at IKKT, it's exactly equivalent to the solution we are running on the CPU. So that means we run exactly with the same number of iterations in IPM. So the speedup translates to the time to solution. It's not only the time per iteration. The solution, I mean, the situation is a bit different for lifted KKT. So lifted KKT is faster, but is less accurate. But IKKT is a bit slower than lifted KKT, but remains much faster than MA27 on the CPU. But it's more accurate. And the second question you had was, let me remember.
So I think you answered it already about the accuracy, but I'm also interested how this compares to the state of the art. So in general, are you faster and similarly accurate, or maybe less accurate? And is there a trade-off there?
if you use lifted KKT, it's less accurate. So the trade-off is it's faster, but less accurate. By that, I mean the tolerance should be loosened to 10⁻⁶ instead of 10⁻⁸. IKKT is as accurate as the CPU, and faster.
Okay, thank you.
It's actually a property of the interrupt algorithm. That will require a second lecture to explain that properly.
Questions? Let's thank our speaker again.
My pleasure.
I'll stop the recording here so we can finalize our chat.
Okay.
Yeah, thank you very much.